of a polynomial function last time. So this time we're going to pick up a different example. And this example, we have the integral from 1 to 2. Gentlemen, we have the integral from 1 to 2 of dy over y, and it might be easier to look at this as being the integral from 1 to 2 of 1 over y dy. I can check. Okay, but you found it, and that's what counts. So we know that the integral of 1 over y is actually the natural logarithm of y, and that's because the derivative from way back in chapter 12, we learned that the derivative of the natural log of x was 1 over x. So if we integrate 1 over x, we're going back and we're getting the natural logarithm of x. So if we're integrating 1 over y, then the integral is the natural logarithm of y. And we're going to use the limits of integration and take the natural logarithm of each limit. So this integral is equal to the natural logarithm of 2, because you always go top minus bottom, minus the natural logarithm of 1. And we can approximate that answer on a calculator. And the answer comes out to be about 0.6931. And I chose that one because the example is one that you need to remember how to integrate 1 over y or 1 over x or whatever it is. And then just plugging in your limits is the main thing that we've added to this. Once you get your integral, your antiderivative, you plug in your upper limit of integration and your lower limit of integration, and you subtract, you find the difference, and that gives you the value of the definite integral. And we can also use, as long as we substitute x for the y, we can also do this numerically. So if we go to math and get the function integral, enter in the function, and as I said, we can't use y, we'll have to use x. So it's going to be dx over x. So actually it's 1 over x, because you have to separate out the dx, and then take that with respect to x, and your two limits are 1 and 2. And you see that you get the exact same answer. Okay, so you can always check your definite integral answers to make sure you got those correct. So our next example is going to be one of those where we're going to have to incorporate substitution, which we learned how to do in one of the last couple sections. And all we're doing here is we're doing a substitution for a problem that we've already done to get the integral, but then we're going to use the limits of integration, 0 and 5, and actually find the area under this curve, which is the square root of 25 minus x squared. So in this case, I'm going to rewrite this as the integral from 0 to 5 of 25 minus x squared to the 1/2 power, and then x dx. And then the substitution comes in because we have a function raised to a power, so this would have been a chain rule problem. So first we need to say, okay, is this the u substitution? Is this u? And the way we can find out if this is going to be a workable u is to see if we can take its derivative. So if this is u, then du, the derivative of that expression, would be 0 minus 2x. Which is negative 2x dx. And we can indeed make this look like that by inserting a negative 2 here, and then also inserting a negative 1/2 on the outside. Okay?
Why do you do that? I don't understand why you make those negative ones.
Because in order to have du, if this is u, if this is actually the integral from 0 to 5 of u to the 1/2 power, du is actually negative 2x dx. The derivative of 25 minus x squared is negative 2x dx. I don't have negative 2x dx. I have x dx. I have this part. So I need the negative 2. If I put in the negative 2 here, I've changed the value of the function. So what I have to do to balance it out, just like I do when I'm solving an equation, I can't put something in if I don't take something out. Since I multiplied this by negative 2, in order to balance that out, then on the outside I'm going to multiply by negative 1/2. Negative because I need to make that back into positive, and 1/2 because 1/2 times 2 is 1, so they cancel each other out. Okay? So now that I've done that, I have this integral. So in that case, then what I need to do is I'm going to actually do the integration of u. I'm going to treat it as if it's a u problem. So this tells me that I'm actually doing negative 1/2. And if this is actually u and not x, then plugging in x here means that when x is equal to 0, this is 25 minus 0. So that means that limit is going to become 25. And then if I'm plugging in 5, 25 minus 5 squared is 0. So the 5 limit for u, the value of u, becomes 0. Now this is one way to do it. There's actually 2 ways to do this problem. Okay, so if you don't understand this way, hang on, you may understand the other way. So this one, when you make the u substitution, you have to change your limits by plugging in x and get the limit for u. That's what we're doing here. I know that may be a little confusing. But again, I'm taking, because this is u, I'm taking the bottom limit and plugging in 0 for x and evaluating 25 minus x squared. 25 minus 0 is 25. And then I'm also taking 5 and plugging it in for x. So 25 minus 5 squared is 0. So when x is 5, the value of u is actually 0. And of course, I know then how to do this because this is a power function. So the way that you integrate a power function, and again, I'm going to have to just carry this 1/2 along, is I add 1 to the power, which that becomes then u to the 3/2, and then I take that new power and I divide by it, and then I'm going to evaluate it at 25 and at 0. Now this is pretty complicated, so I think I'd rather try to simplify this a little bit. So I'm going to change that to -1/2 times, and since this is u to the 3/2 divided by 3/2, what I'm going to do is substitute in a multiplication problem and call that u to the 3/2 times 2/3, which will make the whole problem easier to complete. And that's actually what I'm going to evaluate at u equals 25 and u equals 0. So -1 times u to the 3/2 times 2 is 2u to the 3/2 over 2 times 3 is 6. And we're going to evaluate that expression when u is 25 and when u is 0, and then we're going to subtract. So it's going to be -2 times, we're going to start with 0 because it's always top minus bottom, and of course what we see happen here is, since we're taking u to the 3/2 power, that's just u to the 3/2. And 0 to the 3/2 power is still 0. So this all becomes 0. And it disappears. Then we have negative times negative gives us a positive answer. And 25 to the 3/2 power, we'll just evaluate that on the calculator. Comes out to be 125. And we're going to multiply that 125 times 2. So that's going to be 250. And then 250 over 6 is the same as 125 over 3. And that's the exact answer. You can change it into a decimal if it was an application problem, but this answer is the actual answer that you get. And again, we can do this integration by using the integral on the calculator, since it's a definite integral. And remember that our actual function is, if we go back to the original problem, x times the square root of 25 minus x squared with respect to x, and And going back to the original limits of integration, we're going from 0 to 5, and we should see the same answer. It's having to think about that one for a little while. And it comes back and it says that's 41.66666, basically 41 2/3. But if you take 125 and divide that by 6, excuse me? Yeah, 25 divided by 3, I'm sorry. Then we get the same answer, okay? So even though we did a U substitution and the calculator used it straight with X, then we did get the same answer with numerical integrals. Now the only hitch in that one, remember, is that when you do the U substitution, you have to remember, this is very important, because if you don't do this, it's not going to come out right. It's very important that you change your limits of integration into limits that are compatible with U by substituting X in and finding the value of what U was. Because the original problem is when X is these two numbers, this problem doesn't have X in it anymore. Okay? Now the second method may be one that makes more sense to you. So we could do the antiderivative first. Let's see, maybe we'll just get a clean piece of paper here and try to do method 2. So what we could do is ignore the fact that it's a definite integral and just do the antiderivative first. So if I just do the antiderivative first, ignore the 5 and the 0, and I take this to be U, then I find that du is equal to 0 minus 2x, or negative 2x, dx. So just like before, because this is substitution, I still have to put in that negative 2. And that means on the outside I have to put in the negative 1/2. But remember, I'm ignoring any numbers at this point. So when I do that integral, this is equivalent to the integral of u to the 1/2 du with a negative 1/2 in the front, just like before, which is negative 1/2 times u to the 3/2 divided by 3/2, which turned out to be 2 times u to the 3/2 over 3. And then multiplying through, that's going to be negative 2u to the 3/2 over 6. And you could even simplify your life a little bit at this point by saying, well, you know what, 2 goes into 6 3 times, and get negative u to the 3/2 over 3, and then substitute back in what u was. Plug back in u. And then if you do that, you don't have to change your limits of integration. If you do that, we know that this integral up here is equal to this. See, and I left out a negative sign, so I better put that back in. So that integral is equal to that expression, and that expression is still an x. So my original limits of integration which were 0 and 5, I can now integrate this expression 0 and 5, beginning with the 5, and subtract. So if I do that, I have negative 25 minus 5 squared to the 3/2 power over 3 minus negative 25 minus 0 squared to the 3/2 power over 3, and 25 minus 5 squared is 0. 0 to the 3/2 power is 0, and 0 divided by 3 is still 0. Minus 25 minus 0 squared is 25, and 25 to the 3/2 power, I think we already can do that pretty quickly. 25 to the 3/2 power is 125. Over 3, and that's negative. So negative times negative is positive, and we still get 125 over 3. So you can do it whichever way you want to. You can either change the limits and just use the u problem, or you can leave the limits alone and not do anything with them until the very end, and then put the expression back in to a form where it's x, and then use your original limits of integration. Which were the 0 and the 5.
On a test, would we need to do it that way, or do we just plug it in the calculator?
You can plug it into your calculator in most cases, because what you'll see a lot on the calculator is that you can use an answer. You don't necessarily have, if it's definite integral, you can tell me the answer from the calculator, okay? But now there are some catches to using the calculator you're gonna need to be aware of, and those are gonna come up today and next time. Excuse me? That part?
So you're saying on the test, you want us to do all this, or are we allowed to use that?
You're allowed to use the calculator as long as you know how. Now, like I said, there is a catch to using the calculator, and I'm going to show you what that catch is. You have to be careful. That's going to come up here in just a minute. You do need to look at a graph if you're strictly going to do the numerical integral on the calculator. You have to be very careful that you do it correctly. So this is where I want to pick up now. Part in your notes that says area. This is the caveat to using numerical integration. If f of x is equal to or greater than 0 on the interval a to b, the definite integral gives the area below the graph of the function y equals f of x. Okay? That's above the x-axis and between the lines a to b. To see how to work around the requirement that f of x has to come out to be positive, look at the graph of f of x equals x squared minus 4 in the slide that I'm about to show you. The area bounded by the graph of this function, and this is what the function looks like. Give you a good look at it first. The area bounded by this function is an area between the x-axis and the function, and it's bounded by the numbers 1 and 3. Now, the thing that's going to happen that you have to be careful about here is notice where that area is. Because the fundamental theorem is built around the area being above the x-axis, and it's going to look at this as being negative area. The negative sign that we're going to get when we do this integration actually simply indicates the area is below the x-axis. And since we know area cannot be negative, what we have to do is be careful to take the absolute value and not give a negative answer. Okay? Now, if you do this integration numerically, then we're going to integrate x squared minus 4 with respect to x from 0 to 2. Well, actually, I think the drawing shows. We're going to start out with 0 to 2. And notice it does give you a negative area. And if you actually just do the integration with the fundamental theorem, it gives you negative area. Okay? There is no such thing as negative area. Area is a positive quantity. So what you have to understand and what you have to know then is that actual area, you're going to have to take the absolute value of it. You're going to have to ignore that negative sign in this case, in this particular case. And the drawing incorrectly shows it going from 1 to 3, but it's actually going from 0 to 2, which would be this area. And it's the same area. The figure in your textbook is not showing you the correct area for the problem that it gave you. But if you did do the integration and went from 1 to 3, it comes out to be the same area. And that's because of the symmetry of the function. Well, actually, no, it didn't. And it should have. I wonder why it thinks that one's positive. And you can see from what I'm looking at, this could lead to some puzzling results. Here's what we need to look at. Maybe that was the wrong graph I was looking at. Yeah, that was the wrong function. I'm sorry. That was the wrong function. That was why it came out differently. See, that was x squared minus 4. Yeah, our function wouldn't have looked like the one that was pictured. So let me see what our function looks like so we can understand why it came out the way it did. Let me put that back up there. And draw a correct sketch of that graph. Okay, so there's a correct sketch of the graph. So what happens is if you're going from 0 to 2, it's all of that area right there. And that comes out to be 16/3. But if I were looking at it from 1 to 3, which is the other one that I put in, I'm looking at the area that's only right here, even though it goes all the way out to 3. And you can see that that is going to be a lot smaller than the other area. So what we got on the calculator here does not make totally no sense. Now let's look at a different example and try to understand why it's important that we should look at a graph before we do any integration. So here we've got a function that we're going to integrate from x equals 1 to x equals 3. So we're going to do the integral from 1 to 3 of this function x squared minus 3x dx, and because this is just simply two polynomial terms, then we don't have to worry about doing any substitutions or anything. So the integral of x squared is x to the third divided by 3, and the integral of 3x dx is 3x squared divided by 2, and then we just add in our limits of integration, which means the way we're going to evaluate this is we're going to put in 1 cubed over 3 minus 3 times 1 squared over 2 minus, oops, sorry, that was what we actually going to minus. So the minus comes here because we should have started with the top. 3 cubed over 3 minus 3 times 3 squared over 3. And 3 cubed over 3 is the same thing as 27 divided by 3, which is going to come out to be 9. And then 3 times 3 squared is again 27 divided by 3, which is also going to come out to be 9. Minus 1 cubed over 3 is 1/3. And 3 times 1 squared is 3, and that's going to be over 2. And this should have been a 2. I'm sorry, that's my bad. Let me fix that. And we'll just do all the arithmetic on the calculator to make our life easier, and then check it with the function integral. So I got one too many negative signs in there. And that's negative 10/3. And because that's negative, we're going to need to take the absolute value of it. And that tells us that this area is 10/3. And then we can check that using function integral. And negative 3.3333 is the same thing as 10/3, and again, we would just assume that that's positive. So we know that we're right. But the thing to keep in mind is if the answer is given as a fraction and they want you in My Math Lab to type it in as a fraction, it is not possible. Well, actually it is possible. My calculator did. It has stubbed up on me not wanting to do a fraction before. But you can actually get it as a fraction doing the numerical integral. So just remember, number one, area can't be positive. Or can't be negative, it has to be positive. I meant to say has to be. Now this is the one that's going to trip you up. And that's why I'm warning you, look at a graph or it will trip you up. This one says to find the area between the x-axis and the graph of x squared minus 4 from 0 to 4. Now here's what I want you to notice. Part of that area is going to be considered by your calculator to be negative. And part of that area is going to be considered, if you're doing it strictly with a numerical integral, it's going to consider part of that area to be positive. And when your calculator sees a negative number and a positive number, it's going to subtract and give you the wrong answer. Now I'm going to expand out this graph a little bit because I've already got that one in there. We're going to go down to, let's see, I'm going to let that go up to about 5. But we're going to need to go up to about 12 so that we can see this graph. Now, if you have not graphed this, you're not going to realize that part of the area is below and part of it's above. So you want to graph it. That's number one. If you try to calculate the area, and we're going from 0 to 4. And since it probably will come out to be fractions, I'm going to ask it to give me a fraction and see if it will. It comes out and it says it's 16/3. Okay, now I want you to remember that. That's the answer that it gave us, okay? I'm going to tell you right now that that is not the right area. The actual area is 16. Not 16 first. Okay? What you have to do is, if you have graphed it, what you realize is that it crosses the x-axis at 2. If you don't graph it, you're not going to know that. But it crosses the x-axis at 2. And 2 is between 0 and 4. And that's what creates the wrong answer. The correct way to do the problem is you have to actually break up, and you're going to do absolute value, but I'm going to ignore the absolute value part till the end. You're going to break up your integral because it crosses the x-axis at 2, because it's between the x-axis and the graph. You're going to break it up and go from 0 to 2, x squared minus 4 dx. And then you're going to add that to the integral going from 2 to 4. Sorry. Of x squared minus 4 dx. You're going to have to figure out if there's an x-intercept between your two limits of integration. And that's going to give you the correct area, because this one is going to give you the pink area. This one is going to give you the blue area. Remember, your calculator thinks that pink area is a negative number. So when it tries to add these two together, that's why it's going to give you the wrong answer. Okay? And you can see that this area is about 1/3 of that area. So what we're going to do here then is we're going to actually do the integration the way that we're supposed to, using the power rule. We're going to start out x squared, the integral is 2x. I'm sorry, it's not 2x. My brain just went to derivatives. I understand how y'all feel. It's going to be x cubed over 3 minus 4x over 1. And this one I'm going to evaluate from 0 to 2, but because I know it's going to come out to be negative, I'm going to be sure and take the absolute value of it and make it positive. And then I'm going to add that to the same derivative formula, x cubed over 3 minus, and I'm just going to write 4x and not put the 1, and go there from 2 to 4. So we're going to plug in the numbers. If x is 0, I hope it's obvious to all of us that this whole expression becomes 0. Because 0 cubed over 3 minus 4 times 0 is still going to be 0. But when we plug in 2, 2 cubed is 8 over 3, minus 4 times 2 is 8 over 1. And 8 over 3 minus 8 over 1 is negative 16/3. And we have to take the absolute value of that. Which of course is just positive 16/3. And then we're going to add to that, we're going to start out with 4 cubed over 3 minus 4 times 4 minus, this is actually the same expression. We're plugging in 2 again. So that's going to be 2 cubed, which is 8, over 3, minus 4 times 2, which is 8. Now remember, that's negative 16. It actually is negative 16. That's the value. But let's see, 4 cubed is 64 over 3. So that's 64 over 3 minus 16, because 4 times 4 is 16. That's 16 over 3. I think I've lost my place. Let's see. And that's actually minus negative 16 over 3. So that's 32 over 3. So this whole thing is worth 32 over 3. And we're going to add that to the absolute value of negative 16 over 3. And since the absolute value just makes that negative 16 positive, that's going to turn out to be 16 plus 32 over 3, which is 48 over 3, which is, in fact, 16. The actual area is 16. Okay? Don't trust function integral if you haven't drawn the graph.
So on the test, how would you want us to run it? Just the actual area is 16?
The actual area is 16. Now you can still use function integral on this one to get the right answer. Okay? You could still use it, but use it with what you've learned here in mind.
Would you do 2 separate function integrals?
You're going to do 2 separate function integrals. You can't use that one. What you have to do, if you're wanting to do this, is you have to recognize that there is a zero, a real zero, between your 2 limits of integration. This is where the problem is because of that 2. So what you do to counteract that problem and still use numerical integration, this is going to come up in the next section too, is you do function integral of x squared minus 4 with respect to x, but go first from 0 to 2, and realize that your answer may come out to be negative. So do that first. Don't try to do this all at one time. Go ahead and hit enter. and it gives you the negative answer. So what you do is say, okay, I know area I can't be negative, so even though it gives me the negative answer, drop the sign, make it positive, okay? Then go do the rest of it. Go from 2 to 4. And get 32 over 3, sorry. Add those two together. And you get 16. So it will give you the right answer, but you have to pay attention to whether or not you need to make that adjustment in your limits and break it up into 2 functions, okay? And the only way that's going to happen is if you actually graph what you're looking at on a viewing window that includes all of your x, all of the area that's between the lower and the upper limit of integration, okay? So you may have to fiddle with calculator a little bit to get the graph, but you want that graph. You're going to need to check your calculator graph. Okay? Okay, let's go back to the function. And I'll talk to you about this in a minute. But remember, the function, the one we're looking at, was x squared minus 4 dx integrated from 0 to 4. So if I wanted to graph that to make sure of how I needed to approach this, what I'd do is I'd go to y equals and I would enter in my function. That'd be my first step.
Just x squared minus 4?
Yeah, just x squared minus 4. What you do is you enter in the function everything that's there except for the dx. You ignore the dx. Okay? Then you go to your window and you need to make sure that your window is set up to where it includes from 0 to 4. And what I usually do is I try to go to 1 less than the lower limit to 1 more than the upper limit to be sure that I can see anything that happens in between those. So that's why I went to -1 and up to 5. Now actually you can let your calculator set the rest of this. In fact, I'm going to do that now to show you how you can at least get a ballpark graph. So I'm going to hit zoom and do the zoom fit. So it's going to pick those x coordinates and it's going to find me a y window where I should see the graph. And it actually did a pretty good job if you look at it, because it's showing me from 0 to 4. And I know that what the area I'm looking for is, it's the area from here all the way back to here. So it's the area under the curve here that's above the x-axis, but it's above the curve and below the x-axis here. And if I needed to find out where that 0 is in between, because if there's a 0 in between, that's when I make the adjustment. So then I go to second trace and choose the 0 and get a little bit to the left of it and hit enter, and a little bit to the right of it and hit enter, and then hit enter again, so it will show me what that 0 point is. And it says you need to break those limits apart in 2.
You said second trace, what?
Second trace, which is your calc menu, and number 2 is the 0. And it'll kind of coach you through the rest of it, because it says left bound, right bound, and then guess. Okay? Now, as for why that's important, let's put this in context of a business application. If that represents an annual rate of profit for a company, and 16/3 represents the total profit for the company over the 4-year period, the integral between 0 and 2 is -16/3. That negative sign, this is why I'm paying attention to that, that negative sign actually indicates there's a loss the first 2 years. Okay? The integral between 2 and 4 is 32/3, which indicates they made a profit the last 2 years because it was positive. So their overall profit actually is 32/3 minus that 16/3, which is 16/3. You have to be careful in an application profit because just because we say, well, area can't be negative, if that area represents a loss, a negative profit, then yes, it can be negative. And in that case, their overall profit for that first 4 years, it really is only 16/3. Okay? Which is what function integral gives you. Because it's looking at this as not area under a curve, it's looking at it as, this is a number. This is an actual number that means something. And the fact that that area was negative tells us something about the total profit. The total profit was negative. Okay? So you still need to know in order to be able to analyze a problem. And the correct answer to an application problem then wouldn't be that the total profit was 16, because it wasn't. Because they had a loss the first 2 years and a good gain the last 2 years, so their overall profit was 16/3 in thousands of dollars or millions of dollars or whatever. Okay?
So they gave you the profit, but it did not really good income.
Right. So that's why also it's important to graph your problems. If you don't graph them, you're not going to realize, let's say that we're talking about this is revenue, or this is profit, or this is cost. If you have something negative, that means for some, something's going wrong. And usually that going wrong is going to happen with profit, because you don't have negative revenue and you don't have negative cost, but you certainly can have negative profit. So just a quick review. This is the way that you find area, and it doesn't matter if it's an applications problem or what it is, you always sketch a graph, the way that I just showed you. You always, doesn't have to be a beautiful graph, doesn't have to be perfect, but you always look at that graph. You find any x-intercepts that are in the interval from A to B, because those x-intercepts are important. And then divide the total region into the subregions. And if you're just doing the definite integral, it's not an application, then you take the absolute value of all of those little integrals and add them up, because it's going to total that up as area. But if it's an application problem, then any areas that are below the x-axis are counted as negative, and any that are above are counted as positive. But numerically, the area is the sum of all the areas and all the subregions. And even in applications, it's still the sum of all the areas, just taking into account some of those areas might be negative. So here's one on natural gas consumption that we can do fairly quickly, because this is not a hard problem to do numerically now. So this is our problem that we're going to do an integral. We're going to read the problem. It says the yearly rate of consumption of natural gas in trillions of cubic feet for a certain city is given by this function. T is the time in years, and T equals 0 corresponds to the year 2000. At this consumption rate, what was the total amount the city used in the 10-year period from 2005 to 2015? So that's T equals 5 to T equals 15. And what we're doing then is we're going to do the integral from 5 to 15 of t plus e to the 0.01t, and of course that's dt. And this doesn't require any substitution because it's sum of two terms, and one of them we're going to use the power and the other one we're going to use the integral of e. So this actually turns out then, if we don't have any zeros between here and here, it turns out to be a fairly simple problem to do numerically or with an integral. But we need to graph that and see what it looks like. So we're going to go to y equals, and the calculator turned itself off. We're going to go y equals, we're going to enter in t, or we'll have to use x plus e to the 0.01x and we need to graph that from 5 to 15, but I think I'm going to graph it from 0 to, let's say, 20. Just so I can kind of get an idea of what that looks like. So then I'm going to go zoom 0. Let it find a window where at least I can see something. And that looks almost linear. Okay? Let's see what the window is that it shows. It says, okay, it actually put the x-min at 1. I will just assume that it actually start at -2, so I can at least see the x-axis or something like that. Let's see. Let's make it -5. And it's going up to 21. We can go up to 25 and look at it again. So here's the graph. And the part that we're interested in is going to be the part between 5, which is here, and 15, which is here. And nowhere in between there do I see it cross the x-axis. So as long as I don't see it cross the x-axis, I'm good. I'm golden. So that means what I'm actually going to do is I'm going to do this integral the way that I normally would. Now, I can use function integral and just feed it the function, which is again x plus e to the 0.01 x power. Have to close that parentheses. With respect to x from 5 to 15, close parentheses. I don't think fractions matter here. I think we can do with a decimal just fine. So we'll get a decimal answer. And it comes out to be 111.05. Which, since we're talking about trillions of cubic feet, that 0.05 trillion cubic feet is not something we're going to worry overly much about, because this is, you know, kind of a rough estimate anyway. So $111 trillion, be sure and use that word, trillion cubic feet of natural gas was used from 2005 to 2015. Okay? And that's actually our last problem for that section. And we've got 1 minute left, so does anybody have any questions? So answer your question again, Matthew, yes, you can use function integral on your calculator.